Welcome to today's Trane Engineers Newsletter Live program. I'm Jeannie Harshaw, and today we'll be discussing what demand response means for commercial buildings. We'll begin by providing a definition of demand response and why future energy demands call for it, then move into the evolution of the markets and products to provide an understanding of the opportunities currently available and future opportunities. To present this information, today we have a team of energy experts. Matt Bai, Manager of Utility and Grid Solutions, is joining us along with Chuck Laniger, Energy Operations Director. And you all know Susanna Hansen, one of our systems engineers with expertise in energy management. And Trevor Jolson, an account manager from our Energy Supply Services team. But before we jump right into demand response, let me cover the components of electrical power in general. Now, a common way to think about electrical systems is in terms of three main components: generation, transmission, and distribution. A generator converts one form of energy, like mechanical energy, into electrical energy. The output voltage of even the largest generators is relatively low, typically less than 15,000 volts. A transformer steps this voltage up before injecting the energy into the grid. To limit line losses, the transmission grid operates at much higher voltages, usually over 100,000 volts or 100 kV. Some systems operate as high as 765 kV. Now, these high voltage and extra high voltage transmission lines carry electricity for long distances until it reaches the area closer to where it will ultimately be used. Once it's close to its destination, transformers step the voltage back down so that it can more safely be distributed to cities and neighborhoods. The term distribution typically refers to anything less than 35,000 volts. Now, one of the most important and challenging characteristics of electricity is that it cannot be easily stored in large quantities. Once it's generated and put onto the grid, generally it must be consumed immediately. So maintaining the balance between generation and consumption, which can also be thought of as supply and demand, is a key function of utilities and grid operators. Now, while it might be possible to do all of the balancing with the supply side, it's not always practical or desirable. And this is one reason why there is a monetary value for demand response: the ability to balance power by adjusting demand. So Matt, now that we have that set up, can you walk us through the definition of demand response?
I'd be happy to. The Federal Energy Regulatory Commission, or FERC, in Order 719 defines demand response as a reduction in the consumption of electric energy by customers from their expected consumption in response to an increase in the price of electric energy or to incentive payments designed to induce lower consumption of electric energy. In other words, customers are paid or incentivized to change consumption at certain times. Many times the incentives are to reduce load at traditional peak times like a hot summer afternoon. However, as we explore today, the time of load shift may also be changing. Utilities are classified by different ownership structures. There are over 3,200 electric utilities in the United States. Most customers are served by what is known as an investor-owned utility, or IOUs. These are for-profit companies, and they're usually publicly traded. Other utilities are operated by the city they serve. These are called municipal utilities. Others are owned and operated by and for their members, electric cooperatives. Co-ops developed in the early days of electricity in what were then rural areas to serve farms and smaller communities. In addition to utilities, there are umbrella organizations that oversee the high voltage power grid. In some areas, these organizations also operate a centrally managed wholesale electric market. These organizations are called Independent System Operators, or ISOs, or Regional Transmission Organizations, RTOs. ISOs and RTOs were established by the Federal Energy Regulatory Commission primarily to ensure the reliability of the electric system and to provide fair and open access to the system for all participants. This is where demand response comes into play. A key function of all utilities and the ISOs and RTOs is to balance the supply of electric generation with demand from end-use customers, and obviously it is better if they can do this at the lowest cost possible. Demand response is an important tool in meeting this objective. And by the way, for simplicity today, we will be referring to ISOs and RTOs generically as grid operators. Chuck, can you talk about why we need demand response to create that balance?
Okay, so we've introduced the key players: the electric utility who distributes power locally, and the grid operator who manages power supply over a broader geographic region. And we've covered the concept of power balance, so let's look at why balance is so necessary. Without balance, there's no reliability, and the grid operator's main responsibility is reliability. Reliability means keeping the lights on. Grid operators control the transmission system and dispatch power across broad geographic regions. They have to deal with large-scale issues that affect millions of customers. For example, this is a satellite photo of the lights of North America on a typical night. And this is a satellite photo of the 2003 Mid-Atlantic blackout. The blackout started because a generator in Northeast Ohio tripped offline, and power started to flow in from other areas to make up the difference. Then a major transmission line failed, and the remaining lines became overloaded. Eventually, this overloading cascaded until it was finally stopped by isolating almost the entire Mid-Atlantic and New York areas from the grid. Otherwise, a blackout could have spread as far west as the Rockies. So could demand response have prevented the blackout? Maybe not, but this didn't occur all at once. It cascaded over a period of a few hours, with more and more lines tripping offline as time went on. Had broad-scale demand response been available in 2003, it might have allowed system operators to limit the damage to a much smaller area, maybe just northeastern Ohio. The grid operator also coordinates investment in infrastructure so that the system can not only meet today's loads, but also the projected growth of the region. Demand response can help them to avoid or postpone significant capital investments. Utilities need demand response too. In areas with a grid operator, the utility only controls the distribution, the lower voltage side of the transformers, and on to the customers. This section of the system can also have issues of balance. While utilities are concerned about and affected by regional issues, they deal more directly with localized problems. Some examples of the things the utility deals with are localized outage of power lines, a result of storms or overloading. Another reason for demand response is the cost of purchased power. This is especially important for smaller municipal and co-op type utilities who may not own any generation, and so they buy their power from larger utilities or from the wholesale market. The third reason is to delay infrastructure investments. Like grid operators, the utility has to have enough capacity on their system to meet current and future customer loads, and demand response can help avoid or reduce this investment. But the financial, regional, and local issues are not the only pressing concerns facing the power industry. Susanna is going to discuss renewables and their growing influence.
Thanks, Chuck. I'd like to talk more specifically about a challenge that more and more of the power industry is facing. A challenge that definitely affects those key things that Chuck mentioned: reliability, availability, and cost effectiveness. Now, that challenge is how to reliably incorporate renewable energy sources such as wind and solar. While we continue to collectively embrace transitioning off fossil fuels, the fact of the matter is that renewables are not all that reliable compared to traditional power sources. First, let's talk about wind. Now, today's utilization of wind renewable assets during peak events is 20% if we're generous. This graph shows that during the most critical peak demand hours of the year, most wind capacity is unavailable. Think of a hot and muggy summer day when there's no wind. Only 14 to 18% of the designed wind capacity was operating during the top 10 peak demand days in 2012. Consider that 90% or more of conventional generation capacity is typically available during these same periods. Now, wind is just one form of renewable energy. Let's look at solar next. Whether solar energy is produced by lots of homeowners with photovoltaic panels or from large-scale solar collectors, it has the same problem. It only happens during the day. Now, this is probably okay in the summer when we have lots of electrical consumption, but it may not be okay all year. The grid has long been taken for granted as the backup for solar and wind. Homeowners don't typically have batteries. They have an interconnection and rely on the grid when their consumption exceeds their generation. The classic so-called duck curve demonstrates one of the challenges from raising the portion of our energy that we get from solar. The duck curve graphs the net load to the grid over the course of a day. Planning for a net load of 12,000 megawatts at 2 p.m. but a net load of 27,000 megawatts just 5 hours later is really, really difficult. Now, this issue keeps our utilities, RTOs, and producers awake at night, or in this case, stops them from napping in the middle of a beautiful, cool, sunny day. The kinds of days people enjoy for a good portion of the year in some of our most populous states. Cool, sunny days give us lots of solar energy, but not a lot of air conditioning. This issue is one perverse impact that renewable generation may increasingly have. Renewables risk oversupplying energy, which is often immediately followed by a steep ramp, an abrupt increase in demand that can no longer be met by solar energy. This potential shortage occurs because renewable energy output can drop precisely when it's needed most. In fact, some research indicates that weekends have an even steeper evening increase than weekdays. The duck curve was originally noticed in California, but it has started in Hawaii and will be in place by 2020 in North Carolina. Arizona, Nevada, Texas, Minnesota, and Georgia are a few of the other states that need to prepare for potential oversupply and steep ramps. Demand response has traditionally been about utilities and grid operators asking for a reduction in power consumption, and in fact, that was clearly included in the definition. But as intermittent generation, like from wind and solar, start to make up an increasing fraction of power generation, demand response may be used to address oversupply, and may be driving utilities and grid operators to ask explicitly for an increase in power consumption, or to price power very cheaply during the oversupply. So that brings us to the financial impact of renewables. When grid operators are faced with oversupply, and especially if there is a high likelihood of a peak in just a few hours, they start having to pay utilities to use it. Some power plants can't be easily turned up or down, so they have to stay online. The way that customers are encouraged to use the power is through a combination of techniques that we can loosely categorize as a demand response event. Now, this can be great news if you know that it's coming and you're prepared to use cheap power. We're going to talk about specific ways to anticipate in the next sections. The bad news is that grid operators who know these events will occur might raise their peak rates in order to compensate themselves financially. Utilities pay the higher rates to the grid operators and then pass the increases along to their customers. Having a plan and the right system in place is key. So not only do you get paid to respond to an event like this, but you may be also able to use it to reduce your on-peak consumption during the critical period that follows the event. You can multiply the financial advantages and lower the risk of a power disruption. Demand response and energy storage of all types provide grid operators tools or assets to store the overproduction of renewables that can later be dispatched to reduce the peak that follows once solar drops off. Thermal storage, compressed air storage, and batteries can be charged with excess wind at night or excess solar during the day, which helps the utilization of renewable assets. While we normally think of cold thermal energy storage as something that happens strictly at night, this doesn't have to be the case, especially as times of oversupply and cheap energy can happen during the day. The system charges when other electric loads are low. This could be when the wind is blowing at night or over the weekend when many commercial buildings are less active. It's important to realize that the duck curve we just looked at came from March in California. It doesn't reflect much cooling demand. The shape of the net energy curve in July and August will be much different. Now, solar likely does coincide with midday peak usage in the summer, thanks to air conditioning. Thermal energy storage for air conditioning is helpful in a number of ways. It doesn't contribute to the overproduction problem. Little to no cooling is being shed during overproduction. It provides opportunities to correct for it, given the proper coordination. It offloads solar resources when they could have the least likelihood of overgeneration, typically when the least economical and dirty power would be dispatched. And energy storage for cooling reduces disruption to a customer's business, so it's more likely to be used than other systems that might be sacrificed in other demand response scenarios. The problem is far from unnoticed. Energy storage is the subject of a significant number of regulatory and legislative policies and actions throughout the United States. The Energy Storage Association and Advanced Energy Economy created this slide as of late 2016 to help people like us keep track of these proposals, regulations, and laws. So as we've just discussed, demand response is important to a lot of businesses and the people who run them. We have several key players in demand response and other similar programs, and they each have their motivations and concerns. But at the core, These concerns can be classified as stability, reliability, and financial. Generators produce the power, grid operators balance and distribute it, and the utility sells it to building owners or their tenants. And it would be silly to forget that this power represents just one input to the bigger picture. Commercial and industrial businesses in particular consume power to make something else. Reducing the cost of energy makes businesses more competitive. Matt, now help us understand how demand response has evolved over the years and what the markets look like today.
Thanks, Susanna. To understand markets, let's look at how markets perform today so we can anticipate and prepare for the future. We'll break it down by residential, commercial, and industrial. Let's take a look at who's participating in demand response. Notice on this graph that less than 1% of the customers that participate in demand response are from the industrial segment. However, that 1% contributes an enormous amount of managed load, well over 6 gigawatts and 54% of the overall demand reduction. Industrial customers are attractive because of their sheer size. A utility only needs a few customers to get a very large benefit. You can see how attractive. The 1% of participants that are industrial pulled in over 40% of the money. Compare that to the well over 8 million residential demand response participants who represent 25% of the peak reduction. However, residential customers are attractive to the utility for the relative simplicity of the loads and the low risk to the participants. Typical residential loads are a water heater or an air conditioner. This simplicity and low risk leads to a high level of automation and predictability. What about commercial customers? Based on this information, it would appear that there is a tremendous potential here. Only 7% of the customers enrolled are commercial and represent only 21% of the peak reduction. Demand response has evolved in its complexity and automation. The residential sector is a great example of where loads are relatively simple while the automation has become increasingly sophisticated. Many people have heard of or have been exposed to demand response programs at home. Homeowners save on their energy bills by allowing the utility control equipment in their homes. The U.S. Energy Information Administration estimates over 5 million commercial buildings are in the United States. Aggregating these buildings into fleets of buildings means they can provide significant opportunities to balance the grid just as large industrials do today. As a matter of fact, FERC estimates that in a full participation scenario, over 188 gigawatts worth of peak reduction is possible using buildings as a resource. That is equivalent to over 2,500 peaking plants. Clearly, there's great potential for commercial buildings. One of the major hurdles with commercial buildings is determining how much load is available. How do we determine what a building can provide and how do we connect? The first step is to collect and analyze a building's energy use data. This data can come from the customer's utility bills or from meter data provided by the utility, or by installing temporary or permanent submeters. From that, we do a high-level review to understand how much energy the building uses and get a feel for the demand response potential. What is the peak demand? What is the estimated building HVAC load? How much of the load might be in lighting, etc. Next, we look at the business profile. What kind of business is this? If it's a school, is the summer load as high as the winter load? If it's an office, areas like servers can't be disrupted. Some programs might interrupt a few times a year, whereas others require more than 10 events. Understanding which type of program is acceptable to the customer is critical. Once a customer has determined their willingness and how they might participate, we model the potential adjustments to find out what they're worth using an energy modeling application, tuned to the data that's available. This gives us the profile of the major building loads. For instance, since many times capacity is called for on hot summer days, we scrutinize the sheddable load in the cooling systems. With the financials in hand, the customer makes an informed decision to participate. We implement control sequences to use during an event. In many cases, it can be as simple as a few global set point adjustments. In other cases, more elaborate automated sequence of operations are necessary. The final step, of course, is to respond when the events are called. We'll come back to this in a moment. Because over 60% of the energy in a commercial building is used by HVAC and lighting, it makes sense to look at those systems as opportunities for demand response strategies. For HVAC, a simple strategy is to perform a global set point adjustment whereby the temperature set point is raised for the entire facility. Or perhaps the building is zoned and certain zones are able to be adjusted. In still other instances, pre-cooling or thermal storage can be used to offset demand response events. As lighting technology has improved, there are new ways to controlling lighting systems. For instance, lighting may be able to be dimmed using control solutions. Or in other instances, perimeter lighting may be able to be turned off. Or in retail situations, perhaps exterior signs or exterior lighting may be controlled. Additionally, each building may have miscellaneous loads like fountain pumps or some of the elevators that can be duty cycled. And finally, with the correct permitting, generators could be used to offset load. Each building represents a unique opportunity to participate in demand response. Using this process, a resort, for instance, could find 300 kW, a hospital might find 500 kW, and the office may find 100 kW. Each building type is unique and requires a tailored approach to automated or partially automated demand response.
Traditional demand response is used for both capacity and energy, which we often call demand and consumption, in units of kW and kWh. But even these have evolved as our capabilities changed. Likewise, the types and the mix of participants are changing too. Now let's dive deeper into the evolution of demand response and the mechanisms for participation, and how rates and voluntary programs converge to create financial incentives. Chuck, how about we start back at the beginning? Demand response isn't really a new concept, is it?
No, it's not. Demand response has been with us in some form or other since Edison opened the Pearl Street Station in the 1880s. Over time, utility metering and communications developed and customers became more aware. Control technology evolved, eventually to the point where utilities and grid operators developed a variety of formal policies and programs to take advantage of the customer's ability to control how much energy they used, and more importantly, when they used it. We started out with basically involuntary blackouts, and have progressed enough that load is now considered a resource on par with actual physical generation. This opens up a whole new world of opportunities for progressive thinking energy users. Early on, demand response was pretty much involuntary. The Pearl Street Station didn't operate 24 hours a day at first. It just ran primarily at night for lighting. As commercial and industrial customers began to connect motors for processes, they had to plan their demand around the power plant's operating hours. Also, when there was a problem, power might be shut off without any notice at all. And this still happens today. In 2000 and 2001, the grid operator in California instituted rolling blackouts to address supply shortfalls, and as recently as the summer of 2016, they were warning of potential blackouts because of a lack of natural gas to run power generators. This last graphic is from a public service announcement that is currently posted on the website for the city of Pasadena. Eventually, Edison and other utilities recognized that a customer's cooperation could help them avoid the serious consequences of a blackout. After all, it takes a long time to restore any system from an unexpected blackout, and that's not good for the utility or the customer. So it wasn't long before most utilities had a process where they would appeal to the civic duty of customers to curtail energy use for the common good. This process is still in use today, and in many areas, particularly for extreme emergencies. Most utilities keep a list of customers with load and location data and have a formal emergency procedure they implement that includes calls for voluntary load curtailment. Of course, if no volunteers step up, the utility will revert back to the previous option. As we all know, social responsibility only goes so far in solving problems, but money talks. Early electric meters only measured the energy used between 2 meter readings. As a result, the very first utilities simply charged a flat rate that was the same for all kilowatt hours. It was easy to bill, but not easy to use for behavior modification. The cost of generating power is not constant throughout the day or even throughout the year. It's more expensive to serve a customer that uses all their power in one huge chunk over a short period of time. With the invention of better meters that could track when a customer uses energy, utilities were able to institute rates that more accurately reflected their actual costs and rewarded or penalized customers for certain behaviors. So they began influencing customers' usage patterns through rates, also known as tariffs. Customers who use a lot of power over a short period of time require more infrastructure. Demand charges allow the utility to better allocate the fixed cost of this infrastructure, generators, transformers, and power lines. So if a customer can spread energy usage out over a longer period of time, he can use this demand response to lower his costs. The cost of generating power also changes throughout the day because not all generators have the same cost structure or operating capabilities. Large generators are more economic to operate over long periods, but they have lots of rotational and thermal inertia and can't change their output quickly. Some of them need hours to get from a cold start to full load. Smaller generators can ramp up their output quickly, but they're much less efficient at converting fuel, and so they're more expensive to operate. This is why when the load is highest, the average cost of generating is also highest, because the overall efficiency is lowest. Time of day or on and off peak rates allow the utility to charge more when the load is highest. And again, if the customer can modify his usage patterns, he can lower his energy expenses. Many utilities also offer a lower rate if customers are willing to lower their demand at the instruction of the utility. These are known as curtailable or interruptible rates. Typically, these rates are reserved for larger customers who can have a more significant impact on the system load. They also place limitations on how often the utility can call for a curtailment or interruption and how long they can require the customer to reduce load. For many years, these rates were used somewhat inappropriately to simply offer a discount to large consumers. Up until the late 1990s, the number of actual curtailments or interruptions could probably be counted on one hand, if they even occurred at all. Customers got used to the lower prices, but seldom if ever had to live up to their responsibility. However, as fuel prices climbed and utility profits fell, the power companies began to exercise their rights under these rates, and that really took a lot of customers by surprise. There are typically two factors that determine the total cost of capacity: the market value of each kilowatt of capacity and the amount of capacity the customer requires. The market value of capacity is set at some kind of an auction where generation owners and other entities offer to sell a specific amount of capacity at a specific price. These offers are ranked in economic order. The grid operator then determines how much capacity will be needed and awards the offers from lowest price to highest price until they have secured enough capacity plus 15 or 20% to meet any unexpected contingencies. Within a grid operator's area, capacity prices will vary significantly from year to year and also from one subregion to another. The amount of capacity needed to serve the load is determined by the expected peak load on the system. To estimate this value in the future, the grid operator relies on history and adjusts for projected load growth. Now let's talk about how demand response can be used to actually generate revenue rather than just energy cost reduction from responsive loads. That is, get paid to adjust their demand, and the value goes to a different portion of the company financials. At this point, I need to introduce the concept of aggregation. Essentially, an aggregation is a pool of demand response customers that acts like any dispatchable power plant that's available. And just like a power plant, almost every grid operator is willing to pay for this ability. If you recall, grid operators operate a wholesale electricity market. This means that they don't deal directly with end-use customers. So in order to pay customers for the value they bring, grid operators introduced intermediaries who function as more than just a middleman. They're responsible for actually providing the demand response service to the grid operator by pulling together customers and coordinating their actions when the grid operator calls for it. These intermediaries go by different names, but to keep it simple, we'll just call them aggregators. Trevor and Susanna will talk more about aggregators later in the program. Typically, there are two basic programs: emergency standby curtailment and economic curtailment programs. Both result in a payment being made to the customer. In emergency standby programs, a customer agrees to reduce load during system emergencies. The situations that can be deemed an emergency are very clearly defined in the grid operator's rules, and the number of times they can call for a curtailment and the length of their curtailment are limited. Otherwise, customers might not participate. If a customer can prove an ability to curtail load, they can receive a payment just for standing by, whether the grid operator ever calls or not. But, and this is important, if a customer commits to emergency standby and then does not respond, there can be significant penalties. So while a customer volunteers to offer this service, performance during an event is mandatory. In an economic curtailment program, customers get to choose how much to curtail and how long to curtail based on an offer they make to or a bid they receive from the grid operator. Typically, this offer or bid takes place a day in advance, and the two parties agree to the transaction and price through the grid operator's electronic marketplace. If during the day of the scheduled curtailment the customer decides not to participate, they will be responsible for purchasing makeup power from the real-time market to replace the power they were supposed to curtail.
Now you may be wondering, how much of this is only available in deregulated energy markets? So let's talk about electricity deregulation and the differences between regulated and deregulated markets and how these differences affect the types of demand response programs that are available. Under FERC rules, there are two major responsibilities for grid operators. We focus so far on system reliability, keeping the lights on. The other responsibility is to provide non-discriminatory access to the system for non-utility generators and loads. Entities that perform only these responsibilities are classified as independent system operators. In some cases, the utility can also serve the function of an ISO, but in many areas, separate entities were formed, and eventually they combined to cover larger regions. Now, in those regions, organizations also developed sophisticated, centrally administered competitive wholesale marketplaces. Now, in such areas, the entity is technically classified as a regional transmission operator, but many, ISO New England, for example, retained the phrase ISO in their name. So you can see why we are calling them grid operators. It avoids confusion. This map shows the major RTO-operated wholesale markets in the United States and Canada. As we look at the next map showing states where electricity is deregulated, you will notice the relationship between wholesale RTO markets and retail deregulation. This map highlights the states which have a deregulated electricity market, where end users can competitively shop to buy their power supply services from a third party. If you look back at the previous slide, you would notice that all of the active deregulated markets are located in states where there is an RTO-operated competitive wholesale market. This is no coincidence. For competitive retail markets to work, there must first be a competitive wholesale market. In a regulated market, the utility is vertically integrated. They own, control, and are responsible for all three components of the electricity system: generation, transmission, and distribution. But in a deregulated market, these functions are broken up. In deregulated markets, generation can be owned and supplied by any number of entities. It could be a completely different independent company that just sells power to the grid, and it could be a power marketer who owns generation and uses the grid to deliver it to end-use customers. Or it could be the utility for customers who decide not to choose a third-party provider. In these markets, the grid operator does not own or physically operate the power plants. They direct the operation of the generators. They are deciding which generator should run based on their economic costs and operating characteristics. Generators who don't follow the RTO's instructions are punished financially. The transmission system is also operated by the grid operator, but again, they do not own or maintain it. They coordinate all maintenance and new construction and also maintain a long-term plan to meet future loads. The utility still owns and maintains the distribution system, and most importantly, the utility has the legal obligation to deliver the electricity to the customer, no matter who they choose as their supplier. So no matter the business structure, utilities and grid operators need demand response to balance load and generation, to provide stability during emergencies, to provide a cheaper alternative to higher price generation. And in regulated states, the utility is the only opportunity. In deregulated states, both the utility and the grid operator present opportunities. And in both situations, there are opportunities to reduce costs by controlling demand. In RTO deregulated markets, there are also opportunities to generate revenue. And the names of the programs change slightly too. In regulated markets, we look to tariff management, perhaps like we would negotiated power purchase agreements in deregulated markets. Demand response in regulated markets is expanded into a broader concept of peak load management in deregulated areas. And none of us could think of a way that businesses could actually make money from utility programs in regulated markets, like the concept of demand response aggregation allows in deregulated markets.
Thanks for that level set on energy market structures across the United States. Let's look at the current demand response opportunities available to commercial and industrial energy users across the country. Susanna, you did a great job of breaking down the supply chain of electricity from power plant to building. Let's go ahead and bring that graphic back up before we dive into the different opportunities in regulated and deregulated markets. The players most certainly change with the state's regulation, but what doesn't change is that companies have to make and move power based off the demand of their customers. As referenced earlier, these companies understand basic business principles, and they always use their lowest cost resources to meet their customers' needs first. The cost, or if we look at it another way, profit decline, to meet that highest peak of demand is a burden shared across the supply chain of regulated and deregulated markets. To mitigate and/or to displace this cost, some degree of demand response has been initiated across the country. We just might not always know it when we see it. To make sure we're aware of the demand response opportunities available to commercial and industrial end users, we'll spend the next few minutes exploring explanations and examples of how demand response options present themselves in different energy market structures. Building owners and operators have an opportunity to participate in demand response through their local utility. Local wires companies are establishing demand response programs within their rate structures to help them reduce operating costs and achieve local, state, and federal objectives. In almost all circumstances, a demand response opportunity with a local utility comes as a cost reduction as opposed to a revenue opportunity. Recently, Chuck, Matt, and myself all went to a conference for North American utilities where it was clear and apparent that demand response programs were going to become more and more prevalent at the local level. The insights on the market development from that conference were actually one of the driving forces of the development of this training and our organizational investment in creating demand response opportunities for our clients. In the vast majority of North American utilities, there is an electricity price structure option with a demand component. In this case, customers are assessed electricity service charges based off of their account's peak power demand over a period of time, typically a billing month. This demand charge is a proverbial stick used by utilities to create a desired outcome, in this case, efficiency. Demand charges are becoming the predominant pricing methodology for utilities because of the aforementioned concerns around generation capacity. Markets with large renewable energy commitments are particularly shifting to demand-centric pricing structures for reasons Susanna mentioned earlier. As an example, SoCal Edison, the utility covering the southern region of California, as the name may suggest, charges their customers who use between 500 and 1,000 kilowatts $37.12 per kilowatt in the summer months, as you can see on the sample invoice. Under this rate structure, the demand to run chillers and pumps for an 800-ton chiller would cost nearly $25,000 during summer months. Local utilities are also offering programs for end users to participate in demand response. For an example of such a program, we can visit the Commonwealth of Kentucky, where the local utility to the Louisville market area is LG&E. LG&E is a vertically integrated utility covering generation, supply, and transmission, and fully regulated by the state. They market a program that offers large commercial customers who can obligate 50 kilowatts or greater up to $25 per kilowatt on an annual basis for being able to curtail load in June, July, August, and September. This program supports supply concerns related to diminishing coal capacity and generation within the state of Kentucky. To bring those numbers to life, let's consider a hospital with a peak demand of 3,000 kilowatts. By reducing their peak demand by 20%, if and when called upon, they will receive $15,000 in annual rebates from the utility. We'll talk more about the strategies that can be implemented to get to that short notice 20% demand reduction, but spoiler alert, there are a few paths to get there without affecting critical operations. Some utilities are also working with commercial and industrial customers in a more connected fashion. In the Tampa area, the local utility, Tampa Electric Company, will pay $3.50 per kilowatt per month for equipment they can directly connect to and issue a temporary power interruption in an emergency need. Residential programs have existed like this for years. Utilities like Tampa Electric are looking to make the commercial and industrial programs more hands-off for customers as well. Not all utilities are at this point though, and not all customers are comfortable giving this kind of control to their utility. Quick-serve restaurants, especially multi-site operations, have shown interest in this level of control. A franchisee with 10 burger joints in Tico could participate their rooftop units in the demand response program to create a $12,000 annual cost avoidance. This is nearly a 5% discount on all electric cost with very limited and seldom noticed service disruption. Now, $12,000 might not sound like a lot, but to the bottom line, that's the equivalent of 200,000 burgers sold.
Thanks, Trevor. To summarize so far, commercial and industrial customers across the country have an opportunity to participate in demand response through their local utility. In almost all cases, demand response with a local utility comes through as a cost reduction or a rebate on a bill. Demand response could be as simple as managing your bill demand component to reduce your monthly energy costs. More and more, though, we are seeing local wires companies develop and market programs that incentivize very specific customer actions for more precise time periods. The outlook remains bullish that programs will be made increasingly available across the country. A thorough understanding of local utility rate structures and available programs is essential to optimize building operational cost. So this has all been about cost savings. What about generating revenue? Trevor?
Well, grid operators highly value demand response resources because they allow them to fulfill their ultimate responsibility of grid reliability without having to contract for or dispatch additional non-financially prudent generation resources. Essentially, the pool of demand response acts as its own last resort power plant. In this section, we will focus on using demand response to actually make money, not just save money, in deregulated markets with a functioning grid operator. Grid operators balance load and supply resources 24/7 with products that are traded in markets or produced by the utilities themselves. The product names vary from market to market, but generally fall into the following categories: capacity, energy, and ancillary services. You will notice that each product has different response times required from an asset. Events can be scheduled, dispatched hour ahead, or even very near to real time. Traditionally, these products were produced using standard generation resources like a power plant. However, the resources that can supply these grid products are broadening as technology and markets evolve. Grid operators see an opportunity to achieve reliability and drive alternative efficiency objectives by reducing the demand side of energy as opposed to increasing the supply side. The opportunity can be realized as revenue to buildings. This is achieved through the commitment of capacity and energy. In a deregulated energy market, where electricity supply can be competitively sourced through third-party suppliers, typically with a minimum participation of 100 kW of load response, grid operators will provide payment for making capacity and energy available as demand-side load to be reduced in a dire market-wide need. In order to participate in demand response, building owners and operators will reach an agreement with an aggregator or curtailment service provider like Trane, who can competitively bid a capable load shed into an auction for demand response assets. This aggregator's role is to work with the end user to identify how much a building could participate in the event of a call for demand response. This will include considerations for different time periods and different seasons. Once the customer is comfortable obligating an amount of load shed capability, the aggregator will then look to maximize revenue in local grid operator demand response auctions. Aggregators receive payments throughout the year based off of the availability of the demand response resources, whether an event is called or not. It is more often than not that an event is not called within a season, and the aggregator will receive payment for having load on standby. If an event is called or an annual test is issued, the aggregator will be responsible for ensuring the end user effectively sheds the load within the time allotted, typically 10, 30, or 60 minutes. If the obligated load is shed, the grid operator will issue payment. If the demand reduction is not met, no payment will be issued, and the end user will potentially be assessed a penalty and/or have a period of time in which they cannot participate.
Now, you may have noticed that Trevor has been referencing the aggregator receiving the payment. In deregulated markets, you must contract with an aggregator who is registered with the grid operator and who will receive payments on your behalf. The aggregator will then pay you based on the terms of your agreement, typically a percentage split, with the majority of revenue going to the end user. When selecting an aggregator, the main considerations for a building owner or operator are the ability to partner with you to identify load shed opportunities and the percentage split offered. A typical split is 75% of revenue to the building and 25% to the aggregator, but this can change with negotiation and increased participation. Now let's look at a few examples of different building types and how they have captured revenue through demand response in a deregulated energy market.
Our first example will be in PJM, which is the largest wholesale electric grid operator in the United States. PJM, which stands for Pennsylvania, Jersey, Maryland, but includes more than just those states, spans from the eastern seaboard over to Illinois, where it includes the Chicago electric distribution provider, ComEd. In PJM, more specifically the eastern part of Pennsylvania, a local high school was able to establish a demand response strategy for the summer. The strategy focused on the summer period and included shutting off lights and cycling their chillers to capture 200 kilowatts of curtailable load. The 2016 participation of this load response resulted in $4,200 annually after the aggregator took their 30% share. Let's take a look at how the operational and financial flow worked in this scenario. First, the school contracted with an aggregator and negotiated a split in which they would receive 70% of all revenue. The school and aggregator worked together to identify that 200 kilowatts would be a reasonable amount of demand for them to be able to drop if called upon during the summer. The aggregator bid the 200 kilowatts into the PJM capacity auctions for the summer period, which runs from June through September, and the auction resulted in payments of $30 per kilowatt, or $6,000 in potential revenue. The aggregator was called in May for a test event for the high school. They sent a notification to the facilities manager at the school, who effectively reduced their demand by 228 kilowatts. There were no demand response events called by PJM during the summer period, so all loads that passed testing were paid for being on standby. Our second example of deregulated demand response opportunity will be in the great state of Texas, my home. The wholesale electric grid operator serving the vast majority of Texas is the Electric Reliability Council of Texas, but its friends simply call it ERCOT. Because of the weather, ERCOT deals with extreme peaks during the summer, with HVAC load during 100-degree Texas days being the major catalyst. ERCOT does proudly boast 18,000 megawatts of wind power generation capacity, or roughly 25% of their all-time system peak. However, as Susanna mentioned earlier, wind generators have low performance during summer afternoons, putting even more strain on the system. A large industrial was able to align with the ERCOT market to produce over 2,000 kilowatts of around-the-clock load response. Their load response strategy is to deploy their on-site backup generators if and when a demand response event is called. Interestingly, they view their participation in demand response as risk management because they see a demand response event as a potential for a brown or blackout, and they would like to switch to backup generation as soon as possible. They highly value the advance notice as well as their role in stopping any system failure. For their part, they received $94,000 in annual payments after the curtailment service provider takes their 15% fee. The operational and financial flow is almost identical to the school district in Pennsylvania, but the revenue opportunity is much larger because the amount of curtailable load is nearly 10 times higher and also available throughout the year. Because of this, the industrial was able to negotiate a higher percentage of the revenue to be paid out. The aggregator was paid for the available load 3 times throughout the year, and it was only called once for a winter morning event at 8 a.m. The aggregator received payments from ERCOT of $33,000 in October for performance in the summer period in which no events were called, a payment in February of $36,000 for the winter period for which a single 30-minute event was called, and the industrial end user effectively reduced grid demand by over 2,000 kilowatts by switching to on-site generation and shutting off some lighting. Finally, a payment of $43,000 was issued in June for availability during the fall period, which had no events called. In total, the aggregator received $113,000 in payments from ERCOT, of which they paid $96,000 to the customer. The aggregator made $17,000 for their role, and the industrial was able to capture $96,000 in revenue to help monetize the value of their on-site generation, which they previously had invested in solely for resiliency purposes.
These programs are different from programs available from the local wires companies because of the aggregator's necessary role as the middle person and the fact that a building will have to negotiate their commercial terms with that aggregator. The demand response opportunities available from grid operators and line companies are potentially, but typically not mutually exclusive. Ultimately, demand response through a grid operator presents a unique opportunity to monetize a building's capability, be it the ability to back off operations when called upon during a specific time of the year, like that high school, or the ability to reduce grid demand by shifting to on-site power generation like our industrial example. Now that we know the opportunities that exist for revenue with grid operators, it is important to dive deeper into the opportunities to manage the costs that come from a grid operator, even when those costs are passed through by another company. Similar to how the local wires companies assess demand charges, buildings in deregulated energy markets have grid operator charges that are driven by demand during a period of time. The methodology grid operators use for cost setting is similar yet different than what we've been discussing so far. There's a strategic opportunity for buildings to drive down their annual electricity cost by reducing demand during just a few hours of the year. Just a few hours of the year? Trevor, tell us more about this opportunity.
The two major costs that are assessed by a grid operator are capacity, which is assessed to ensure there is enough generation to meet peak demand, and transmission, which allows the capacity to move across the grid. Customers get billed for capacity and/or transmission costs based off of their coincidental peak demand. You may hear industry professionals refer to this as a peak load contribution, or PLC, but coincidental peak demand is the most descriptive and universal term. Coincidental peak demand is a customer's demand during a grid operator's peak event or events. Each of the major coordinated grid operators has varying coincidental peak demand setting approaches, and you will want to know the method to the madness if you have a facility that operates in one of these markets. Let's break them down with a graphic. The ERCOT market monitors for the peak demand event in June, July, August, and September, and takes a customer's average demand during these four events to establish a coincidental peak demand. The PJM market monitors for the 5 highest peak demands between June and September and takes a customer's average demand during these 5 events to establish a coincidental peak demand. The MISO market, or the Midwest Independent System Operator, which covers Michigan and Southern Illinois, which have the deregulated price structures, has a single coincidental peak in the summer. The northern part of Illinois and the Chicagoland area is in PJM, but has a slightly different methodology for setting a customer's coincidental peak demand, as it looks for the 10 highest peaks from June through September. Finally, both the New York Independent System Operator and ISO New England have a single peak from June through September, which establishes a customer's prevailing peak load contribution. Again, customers get billed for capacity and transmission costs based off of their coincidental peak demand. These costs can be very confusing and are many times misunderstood or forgotten because they are charged through the retail electricity supplier and often get blended into a dollar per kilowatt hour or consumption rate, even though they are ultimately derived from a kilowatt demand-based charge. Suppliers try to make energy buying easy for customers, but our experience in energy purchasing tells us that easiest is not always the cheapest. In many markets, 20 to 25% of a customer's annual cost of electricity supply can come from their demand during just a few hours during the summer. There are 87-60 hours in most years, but just a few can represent a significant portion of a building's annual energy cost. Now that we understand how a coincidental peak event affects a building's annual cost of energy, let's look at some of the strategies we can take to reduce this cost.
The easiest way to reduce a coincidental peak demand is to build up system efficiency headed into the summer. Every effort you take to reduce your demand during the summer periods from 3 to 6 p.m. will have an impact on your future capacity and transmission costs. For example, a higher efficiency chiller would reduce your summer demand for all hours as compared to a legacy model. As a result, you could expect to pay less for electricity supply in the future. As a more dramatic example, you could have a thermal storage system connected to your chiller, which reduces your summer afternoon demand all days. As a result of this system, you could expect to pay significantly reduced electricity supply costs because you have mitigated the grid operator cost component. Remember, the grid operator is concerned first and foremost with reliability of the grid. If your building makes investments that would support the grid operator in achieving this objective, you will be rewarded with lower cost. When designing a building or an energy project, it is critical that we include grid operator costs into the equation so that we are effectively evaluating costs and returns. While the passive approach allows you to benefit from all investments in efficiency, many buildings are taking a more active approach in managing their coincidental peak demand. An active approach leverages intelligence into when the grid operator peaks could be taking place and then looks to reduce building demand during this time. This strategy provides a cost reduction for an entire year for reducing demand for just a few very targeted hours. The intelligence of when these events are going to take place typically comes from your energy supplier or a consultant like Trane. The peaks can be identified by monitoring weather patterns, generator dispatch, and other local market factors. Generally speaking, though, the events are going to happen on the hottest afternoons in the population centers of the grid operators. Historically, the coincidental peak demands take place between 3 and 6 p.m. because there is a collision of industrial, commercial, and residential demand. The active approach can be just a small change compared to the more passive methods. Reducing loads during the times when capacity and/or demand charges are determined can be built into the system design, or they can be dynamically or operationally performed when these peaks are likely to occur. Let's take that known issue of 3 to 6 p.m. in the summer. For example, if you have a thermal storage system, you're already reducing your cooling load using it on the summer days between 3 and 6 p.m. You likely already have a lower capacity charge than you would have had if you didn't have thermal storage. This is sort of passive because you already do this every day and not in response to a signal of any kind. You're also typically not compromising any operation of your facility. You have the same set points and the same cooling as you would have had without thermal storage. Similarly, any upgrades that you do to your energy-consuming equipment, such as chillers and lighting, will lower the peak demand and also reduce capacity charges. But it's also possible to run some of these more passive systems differently in response to a signal from the utility or the grid operator. If thermal storage were used slightly differently on the peakiest of the peak days, and you save some of the stored energy for the afternoon, you could deploy more aggressively if and when they call for it. Trevor, walk us through a specific scenario when a customer was able to strategically reduce their coincidental peak demand to reduce their annual electricity costs.
Happily, a commercial office building in Boston was looking to better understand why their future electricity pricing was going up. They ultimately discovered that it was because of ISO New England charges for capacity because of recently retired power plants, and that these charges were assessed based on the building's demand during the grid operator's peak in the summer. Well, they knew they couldn't shut their building down altogether. They looked for ways they could reduce demand during the summer. Ultimately, it was determined that a 3-degree change in set point during a summer afternoon would reduce demand by 150 kilowatts. They deployed this strategy the upcoming summer when they received notices that ISO New England could potentially be setting its peak. They ultimately reduced their year-over-year coincidental peak demand by 162 kilowatts and saved over $29,000 a year on their future electricity supply cost. In this case, ISO New England was the culprit for the increase in cost. This was confusing to the building owner because their electricity supplier was the one showing the price increase. Let's look at how this translated to their electricity supply price by breaking down the building profile. Their 2015 coincidental peak demand was 820 kilowatts. Their 2015 annual consumption was 2.8 million kilowatt hours, which is a 40% coincidental peak load factor. The grid operator charges were $15 per kW per month for calendar year 2017. Had they maintained this coincidental peak demand, their capacity cost to ISO New England through their electricity supplier was going to be $147,000 annually, or when blended out over 2.8 million kilowatt hours, just over 5 cents per kilowatt hour. Remember, this is a nickel for just capacity. There are additional kilowatt hour charges. By reducing their coincidental peak demand by 162 kilowatts, their capacity charges were reduced by 20%, or down to 4 cents per kilowatt hour. All this savings for performance just during one 3-hour window the summer before. Major savings for a targeted strategy around a significant local market cost. In a deregulated market, whether your building is in a position to do demand response or not, you are still going to get assessed charges based off of coincidental peak demand. It is important to understand these charges so you can effectively evaluate and implement energy efficiency measures throughout the year. Understanding grid operator charges also presents an active, non-contracted opportunity for demand response, in which you can capture a large cost reduction by dropping your building's demand just a few times during the summer. Let's pull this all together. Demand response is available to all buildings, but will look different depending on where you are. This slide charts the opportunities and the potential upside. End users must consider availability, structure, opportunity size, cash flow, and partner. The most dynamic buildings can establish the lowest operating cost, which can include direct revenue by stacking these opportunities. Next up, Matt is going to talk through how systems use technology to increase automation and where the future may be headed.
Buildings will become more and more accepted and perhaps even expected to provide the services required to balance the grid. Collections of buildings will likely be able to provide all sorts of services that today are being provided only by generation resources. We mentioned that FERC 719 allows buildings to bid into the energy and capacity markets on a relatively even basis with generation. In the future, not only will more buildings participate in these markets, FERC says that they can participate in other services as well, as long as demand-side resources meet the same requirements as other resources. Other services could include ancillary services such as regulation and frequency response. While traditional demand response is active and growing, new control technologies and connectivities providing pathway for buildings to provide more services traditionally reserved for generation. For example, operating reserves with 10 and 30-minute response times, regulating reserves with a 2 to 4 second response time, and frequency response with 12 to 30 cycles response time. Each of these services introduces the need for increasingly flexible and complex controls. The faster an asset can provide the required kW and the less notice required, the higher the value of that asset. This screen shows the requirements that ERCOT places on participating in ancillary services. In many cases, these services are beyond the installed capabilities of most existing buildings and systems. However, it's not too soon to prepare. In the near future, many more buildings will include battery storage, thermal storage, dispatchable on-site generation, and smarter appliances and equipment. Of course, all of this will require upgrades to building automation systems so that these resources can be used more fully and with less need for operators to intervene. While the interfaces progress towards standardization, they're not yet where many of us would like them to be. Today's program has shown us many examples of ways that buildings and the grid can interact already. The only thing that will change is that these techniques, systems, and equipment will only grow in value in the future once buildings interact more transparently with the systems that run the grid.
Thanks for all that insight, guys. So to summarize today's program, there are things that building owners can do today with the systems we already have. We can make money or save money by manipulating energy use patterns. We can pool with others through aggregators to better participate in demand response in deregulated markets. We can work with energy experts who predict peak events and reduce our contributions to the coincidental peaks. And we can install and upgrade our equipment to improve our capabilities today and prepare better for what's to come. So that's it for now on demand response. Ask your local host for a bibliography containing additional resources for grid edge solutions. And check out the latest Trane continuing education programs on demand and free of charge. Visit trane.com/continuing education for a complete list to satisfy credentialing requirements. And don't forget to fill out a survey and let us know what you thought of today's program. And finally, please ask your host for details for next year's Engineers Newsletter Live lineup. Thanks for your time today. We look forward to seeing you next year.